Hey class, today we're going to go over section 2, which is about using the scientific approach. One of the key goal questions that we're going to answer and that I want you to understand from this lesson is what is the goal of the scientific method? So we're going to go over what is the intended purpose of it and kind of a general explanation of what the scientific method is. So to answer that key goal is the goal of any scientific method is to either solve a problem or to better understand an observed event. This can help you answer questions, why do we see things, or why does a certain thing happen? So what is the scientific method? Your book defines the scientific method as an organized plan for gathering, organizing, and communicating information. Now, hopefully you remember from the last lesson that you can gather information in several different ways. One way you do it is usually through your senses. We can gather them based on our sight, smell, touch, hearing, etc. And we can gather this information in two types of data. It can be qualitative data or quantitative data. Qualitative data means it's usually a description, like something's color or its texture. Quantitative data is going to be like a number, so maybe the height or the time. We're going to take all this information and we're going to organize it, and then we're going to communicate what we found based on our information. We can use the scientific method to search for an answer to a question, and one thing to know about the scientific method is that it can vary from case to case depending on the question that is asked and how the person decides to look for an answer. So here is going to be a general example of the scientific method. Each step uses different skills, and one thing to know about this is just a general example. The order of the steps can vary, and I'm going to go ahead and star that because it's important. Sometimes you're going to use all of the steps, and other times you might just use some of them. Also note that not every scientific method is going to start with an observation. You can start anywhere along the scientific method route. They just generally start with making an observation. So let's go through the general approach for scientific method. First is to make an observation. Next, you generally ask yourself a question. You start getting curious. Then you're going to develop a hypothesis. And generally, a hypothesis is like, I think that so-and-so is going to happen. Then you're going to test that hypothesis with an experiment. That experiment is going to get you data, and you're going to use that data to draw conclusions. From there, one of two things is possible. The first thing that's possible is maybe your idea or what you thought was going to happen actually happened. The other one is maybe your hypothesis or what you thought was going to happen didn't actually happen. If your hypothesis was supported or what you thought was going to happen actually did, usually what you would want to do is you would want to redo your experiment to see if you got the same results. That just tells you if you got the same result, that it wasn't just a fluke or a mess up the first time around, and that you're consistently getting the same thing. If for some reason your hypothesis or guess was not supported or was not correct, what you would do is you would go up and revise your hypothesis and then go back through and redo the experiment again. Once you have redone the experiment and you have gotten the similar results over and over and over again, and your idea is supported, that's when you can start developing theories or laws. So let's go through each of one of these individually. First, make observations. Scientific investigations often begin with observations. Often, but not always. Again, scientific method, you don't have to start at a specific spot. An observation is defined as information that we obtain through our senses. So remember your 5 senses. You have smell, taste, touch. You can hear things, and you can, I already said smell, taste, touch, hear. I am missing one. And C. Whew, that took me a hot minute. From there, you can form a hypothesis. And a hypothesis is usually just a proposed answer to a question, or what do you think is going to happen? Typically, we like to write hypothesis by saying, I think because. So an observation I have is when I'm making chocolate milk, oftentimes I add too much chocolate, and when I look in the bottom of the glass, I have too much chocolate left over. So I'm going to form a hypothesis that maybe I think 3 tablespoons of chocolate is better than 4 because I will not have chocolate on the bottom of when I'm done drinking my milk. Then what you would do is you would test a hypothesis from something called a controlled experiment. In this experiment, there are a lot of factors that you can change, and these are all called variables. 2 very important variables are independent variable and dependent. The independent variable is sometimes called the manipulated variable, and that's because this is the thing that you are changing. So the thing you change, or the thing you manipulate. The dependent variable is sometimes called the responding variable because this is the thing that changes because of the manipulated variable. Or in other words, usually this is the thing that you are measuring. What is being measured? These all go into something known as a controlled experiment. Typically, a controlled experiment is an experiment in which only one variable is changed, and that variable is going to be the independent. All the others are kept the same. So any variable you do not change or is kept the same are called constants or controls. From there, from your experiment, you're going to draw conclusions, and this is based on the information that you've gathered for your experiment, and you're going to decide how do those facts or those data apply to what you guessed. So here's an example from your book. The question they asked is, how does speed affect how wet you get in the rain? They hypothesized that the faster your speed, the drier you will be. And the experiment was to test whether speed affects how wet you get in the rain. In 1997, 2 meteorologists actually conducted a controlled experiment to determine if moving faster keeps you drier in the rain. During this experiment, one scientist walked 100 yards and the other ran the same distance. Variables like the type of clothes were controlled. So if we're looking at this, and I would ask you, what is the independent variable? You would have to ask yourself, what did they change? And the one thing they changed is their speed. One ran and the other one walked. If I were to ask you the dependent variable, this is the one you're going to say, well, what changed based on the speed changing? Or in other words, what did we measure? And the one thing we measured is how dry you stay, or basically how wet you get. Another question I could easily ask you are, what are some controls? What are some things that they kept the same? Well, they told you that the type of clothes was controlled. They both wore the same type of clothes. Another thing that they have kept the same is they both walked the same distance. So the same distance. And the last one is they hopefully had the same amount of rain. It would not be fair if one walked out in a downpour and the other one walked out when it was just sprinkling. From this information, they gathered data and they saw that the walking scientist accumulated 217 grams of water, while the one that was running accumulated 130 grams of water. 130 grams is significantly less than 217, so they concluded, based on their information, that running will keep you drier. Now, after this, they're going to notice that it supported their hypothesis, so they should retest this to make sure it wasn't a fluke. In fact, this hypothesis was tested by Mythbusters, and they found the opposite. They found that you don't get as wet if you walk than if you run. Now, remember when we said on a few slides ago, we talked about if something is tested over and over and over again, and we see that it is true, it supports our hypothesis, things can become scientific theories. We also like to use the term scientific laws. So our next key question that we're going to answer is, how does a scientific law differ from a scientific theory? Well, to define a scientific theory, it is defined as a well-tested, because you test it over and over again, explanation. So here's your key word. It explains why we see a set of observations, why something happens. So again, once a hypothesis has been supported by repeated experiments, usually we can start to develop a theory. And that theory explains what we see. A scientific law, on the other hand, does not explain. It can describe what we see, but it doesn't explain why we see what we see. So an explanation is a theory. If you can't explain it, it is going to be a law. So how do we get scientific laws? Well, we get scientific laws the same way we do with theories. We have repeated observations and repeated experiments. Again, the only difference is theories you explain, laws you cannot. A law is just a statement that summarizes what we see. A good example of this is Newton's law of gravity. It is a law because we know that if we throw something up, it's going to probably come down. Gravity is going to pull it down unless it gets stuck on a tree or a house. We know that gravity is a thing. However, we don't know how to explain how gravity works. We don't know how it works. We just know that it's there and it pulls everything back towards Earth. And this is the third and final big topic of this section, scientific models. And our key question is, why are scientific models useful? Well, in order to understand that, we have to know what a model is. A model is a representation of an object or event. A street map is a good example of a model for a city. It tells you the city's roads, the buildings, and where different things are located. In Mrs. Tom's class in the junior high, you use Legos to model basically elements and compounds and mixtures. Now, scientific models, the reason we use them is because they make things easier to understand that might be too difficult to understand, like the idea of compounds, or things that you can't observe directly because they're either too big or too small. A good example of this is airplanes are huge, and before we build them, we like to build models to show what they're going to look like. Nowadays, we have the technology that allows us to build models on the computer, and this helps people that are building the computers or these planes, also known as engineers, to see how the parts are laid out, where all the faults are, where is the control panel, etc. Also, models are very beneficial to help you see things that are too small, like atoms, or things that are too large, like the solar system. Models do not have to be physical, though. They can actually be mental. So oftentimes in English, you hear the words simile and metaphor. They try to give you a description. Those are mental models. If I was going to describe a comet and I say that they're like giant snowballs, that's going to give you the image in your head that they're going to be really cold. They're probably going to be made up of ice and snow. And that's true. Comets are made up of ice. Now, as new data is collected, models can change and be replaced with new models. This has happened over and over and over again, especially with the solar system. First, Pluto was a planet, and then it wasn't a planet. And as we get more information, these models change. So that is the end of today's lesson. Let me know if you have any questions, and I'll be more than happy to help. And with that, I hope you guys have a good day.